Welcome to the Deep Dive, your shortcut to being well-informed. If you ever tried keeping up with finance today, it's just this relentless flood of information.
Oh,
The
absolutely.
old days, reading the paper, maybe a few calls for trading insights, gone.
Long gone.
Now it's vast amounts of real-time data moving so fast, well, faster than any person can track. It's a real challenge, and how do you even make sense of it all, let alone act on it?
Exactly. And the sheer volume, the speed, it doesn't just suggest a different approach, it demands one. It demands a whole new operating system for finance, you could say. Algorithms, machines, they aren't just helping anymore.
They're driving it.
They're driving most global equities trading. It's beyond human scale now.
And that's really our mission today. We're taking a deep dive into Python for Finance by Ives Hilpisch. He's a real master in this field.
He certainly is.
This deep dive is your guide, really, to understanding how this one technology, Python, isn't just keeping up with the data explosion. It's actually, well, becoming the backbone of modern finance. We'll unpack the key ideas from Hilpisch.
Yeah, and the goal isn't just facts, it's those aha moments, So you get a practical feel for why Python is now this strategic platform right across the industry.
From prototyping to production systems.
Exactly. From quick tests to the really complex stuff. Think of it like getting that expert knowledge, but quickly and without getting totally lost in the technical jargon.
Okay, let's unpack that. The first big thing from Hilpisch is, well, it's not even really debated anymore, is it? Python's advantages in finance.
No, it's pretty much settled. Institutions worldwide, they're all leveraging its ecosystem. It's powerful.
So what's driving this massive shift?
It's fascinating, actually. It boils down to these two big intertwined forces transforming finance. First, Hilpisch calls it data-driven finance, which basically means programmatic, often real-time, access to pretty much all financial data. Think about it, algorithms and computers driving most global stock trading. Python's the thing making that possible.
It's the conduit, and the second force builds on that data, I assume.
Precisely. That's AI-first finance. So artificial intelligence, machine learning, they're increasingly used to predict market moves.
Oh.
We're talking about sophisticated tools like TensorFlow, scikit-learn, becoming, standard for spotting trends or optimizing strategies. Python kind of acts as the central nervous system connecting it all.
Right, the glue holding the data side and the AI side together. So what is it about Python specifically that makes it so appealing for finance? Bridging that gap between math theory and actual high-speed code.
Well, it's got several things going for it. It's high-level, object-oriented, features like dynamic typing, dynamic binding. They make it really, really good for rapid application development.
Getting things built fast.
Exactly. And it works great as a kind of glue language. You can use it to connect existing components, maybe written in other languages, which makes integration much simpler.
Okay.
And the syntax, it's simple, it's readable. That means lower maintenance costs down the line, which is honestly huge in finance where things change so fast.
And here's the bit that I think really clicks for finance people. The syntax is incredibly close to mathematical notation.
That's a huge one.
It's a game changer, right? You can take these complex financial algorithms, models, straight off a whiteboard almost, and turn them into working code pretty directly.
Absolutely. It makes that translation so much easier. That's why it appeals so strongly to the quants, the quantitative analysts, and, the scientific developers who think in math.
And it's not just for them, is it? The appeal is broader.
Oh, definitely. It attracts, professional software devs building big, robust systems, but also the scientific types who need to explore data, visualize it, run quick tests, and even casual programmers can grab existing libraries to solve specific problems. It kind of democratizes these powerful tools.
Okay, so Python's the bridge. Let's talk about the foundations. How does it actually handle the data itself? You mentioned dynamic typing earlier. What does that mean in practice?
Right, so Python is dynamically typed, which means the type of an object, like whether it's a number or text, is figured out when the code runs, not before.
Okay.
Think of it like Lego bricks that just kind of automatically fit together as you build, instead of needing to know the exact shape of every piece beforehand. For development, this can make things a lot faster compared to, say, C or Java, where you have to declare all the types explicitly.
Right, less upfront definition work. And even the basic data types in Python, like numbers, integers, and floats, they have some interesting quirks relevant to finance.
They do. Even simple numbers are actually objects in Python. They have methods attached. And here's that surprising fact you mentioned. Sometimes, with standard floats, you do a simple sum like 0.35 plus zero point 0.1, and you might get something slightly off, like 0.449999, ending in a 6.
Why does that happen? Seems like a problem for finance.
It's a classic computer thing, how they represent decimals in binary. It can lead to tiny inaccuracies. But for finance, where you need absolute precision for auditing, compliance, just basic trust, Python gives you the decimal module. This lets you work with arbitrary precision. You can set how many decimal places you need, ensuring accuracy down to the tiniest fraction. Crucial stuff.
And then you've got Booleans, true and false. They're the bedrock of logic, controlling how code flows in if statements or while loops, essential for any kind of decision-making, like in trading rules.
Exactly. And text processing. Python's really strong there too. The basic strop object has useful methods like capitalize, split, but for the really messy stuff like pulling specific bits of info out of news feeds or filings, that's where regular expressions or regex come in. The remodule. It's incredibly powerful for finding patterns, like extracting dates and times from unstructured text. Offers convenience and performance.
Okay, so beyond the basic types, we need ways to organize data, Python's core data structures.
Right. You've got tuples. They're immutable, meaning you can't change them once created. Good for fixed data, like coordinates or maybe database records. Then lists. They are mutable, flexible, great for collections of things that might change.
Like a list of trades.
Exactly. Then dictionaries. These are key value pairs, super useful for mapping things, like a stock ticker to its current price, or instrument properties, very common in finance. And finally, sets. They're collections of unique items, great for, say, quickly finding all the unique stocks mentioned in a report or removing duplicate IDs.
These building blocks sound useful, but the real power, especially for finance, comes when you start doing heavy-duty calculations, right?
That's where we get into the real workhorses.
Which brings us to NumPy and Pandas. Let's start with NumPy, the foundation for numerical computing in Python.
Absolutely. Its core element is the end array, which stands for n-dimensional array. It's designed for two key things. Convenience, yes, but mainly high performance with large numerical data sets.
High performance how?
Well, think about multiplying a list of numbers by, say, 2. In standard Python, if you multiply a list, it just repeats the list.
Right. 1, 2, 2 gives 1, 2, 1, 2.
Exactly. But with the NumPy on array, it does what you actually want mathematically. Element-wise multiplication. It multiplies each number in the array by 2. And it does this incredibly fast, even across millions of data points, because the operations are often implemented in compiled C code underneath.
Okay. That makes a huge difference for financial modeling, simulations, all that calculation volume. And you mentioned universal functions.
Yeah, functions like np.exp for exponential or np.sqrt for square root. They operate element-wise on entire arrays, too. Again, way faster than looping through a Python list and applying the built-in math function to each item individually, especially for large arrays. This whole concept is called vectorization.
Vectorization, got it. Doing operations on whole arrays at once.
Exactly. And NumPy also gives you powerful tools for creating arrays, indexing them in complex ways, slicing out sections, reshaping them. You can even use Boolean arrays of true-false values to select data based on conditions, like pull out all stock prices above a certain threshold. Very flexible.
Okay, so NumPy handles the raw numbers efficiently. Then we layer Pandas on top, the data analyst's best friend.
That's a great way to put it. If NumPy is the high-performance engine, Pandas provides the structure, the labels, the tools for working with, well, structured data, especially time series.
Like spreadsheets on steroids?
Kind of, yeah. It introduces the data frame, which is like a table or spreadsheet, and the series, which is like a single column. The key things are features like automatic data alignment based on labels, like dates or tickers, and really flexible indexing. Hugely valuable when you're combining financial data from different sources that might not line up perfectly.
And you can get quick summaries of your data.
Oh, yeah. Methods like .info give you a concise summary data types, missing values, and .describe gives you quick descriptive statistics, meaning standard deviation, min, max. Really useful for a first look, validating your data, maybe checking if your index is actually recognized as dates, a date-time index.
And specifically for financial time series, Pandas really shines.
Absolutely. It makes reading data from all sorts of formats, CSV, SQL databases, Excel files, JSON really straightforward, calculating things like log returns, which are standard for analyzing price changes, simple, resampling data, like going from daily stock prices to monthly averages, build in.
And technical analysis stuff, moving averages.
Yep. Deriving rolling statistics like simple moving averages is just a couple of lines of code, fundamental for technical traders.
And combining data.
Immense power there, too.
Okay.
Operations like Group B for aggregating data based on categories and merge, join, concat for intelligently combining different data sets. It's really designed for the kind of data wrangling you constantly do in finance.
Okay, this all sounds incredibly powerful, but there is still that lingering perception, isn't there? Python is slow. Let's tackle that. Hilpish addresses this directly.
He does, and it's true. Pure Python code, especially with explicit for loops iterating over lots of data, can be slow compared to languages like C++ or Java. But the crucial point is, it absolutely does not have to be.
There are ways around it. Strategies for speed.
Exactly. Clear strategies. The first, and often the most impactful, is what we just talked about. Vectorization with NumPy. Replacing those Python loops with NumPy's array operations is often the biggest win.
Right, use the optimized C code under the hood. Don't loop in Python if you can help it.
Precisely. It's like sending that convoy of trucks instead of one at a time. Massive difference.
Okay, what else? What if vectorization isn't enough or doesn't quite fit the problem?
Then you look at things like just-in-time or JIT, compilation with Numba.
Numba, how did that work?
So Numba takes your Python code, especially functions with lots of loops and math, and it compiles it down to highly optimized machine code right before it's executed just in time.
Wow.
It can give dramatic speedups, often getting close to C or Fortran speeds, particularly for numerical algorithms like, say, Monte Carlo simulations. You often just add a simple decorator, like at numba.jit, to your function.
Wow, okay. So that targets specific computation-heavy functions. What if you need even more control, maybe closer interaction with C?
That's where static compilation with Python comes in.
Python. Different from Numba.
Yeah, slightly different approach. Python is like a superset of Python that also understands C data types. You can write code that looks mostly like Python, but adds static type declarations telling Python, this variable will always be an integer, or this one's a C double.
Okay.
Python then translates this into optimized C code, which gets compiled. It acts as a bridge, letting you get C-level performance for critical bottlenecks while keeping the rest of your code in Python. It gives you more fine-grained control than Numba, but can involve a bit more work.
Got it. And for problems that can be broken down into independent chunks.
Then you turn to parallelization with Python's multiprocessing module. This lets you run code across multiple CPU cores simultaneously.
So if you have a task like running thousands of independent simulations.
Exactly. You can split the work across however many cores your machine has. Multiprocessing makes setting this up relatively straightforward in Python.
Okay, so computation speed can definitely be addressed. But what about getting data in and out? I/O input-output. That's often a bottleneck too, right? The CPU is just waiting for data.
Huge bottleneck, often. You can have the fastest CPU in the world, but if it's starved for data from a slow disk or a network, it doesn't matter.
How does Python handle this, especially for typical finance tasks?
Well, Hilpish makes a good point about what he calls mid-data. Many financial analytics tasks involve data sets that are, say, up to a few gigabytes. Too big for maybe a basic spreadsheet, but small enough to fit into the RAM of a modern computer.
Okay.
This mid-data size is actually a sweet spot for Python's scientific stack NumPy Pandas. You can load it into memory and perform really fast analysis. The key is optimizing how you read and write it.
And what if the data is bigger than memory? Terabytes of tick data, for example.
Right. For truly massive data sets, you need something more advanced. That's where PyTables comes in. Yeah, it's a Python interface to the HDF5 data format. HDF5 is a standard designed specifically for storing and managing huge amounts of scientific data. PyTables lets you interact with HDF5 files from Python.
And what makes it good for large data?
Several things. It optimizes I/O operations. It supports data compression, which can save a lot of space and sometimes even speed up reading. It allows for indexing, so you can quickly access specific slices of data without reading the whole file. And crucially, it supports out-of-memory computations. You can perform calculations on data sets much larger than your available RAM.
Wow, okay. So you can handle pretty much any scale of data problem with the right tools in the Python ecosystem.
That's the idea. From small files to massive HDF5 stores.
So we've got the data handling, we've got the performance strategies, but finance isn't just about speed and data structures, is it? It's built on math, statistics, modeling uncertainty. How does Python support the scientific rigor needed?
Oh, hugely. I mean, finance today is essentially applied mathematics and statistics. Python provides the tools to implement these ideas directly. Take approximation, for instance.
Like fitting models to data.
Exactly. We use techniques like regression, think-OLS, ordinary least squares, a real workhorse for finding linear relationships or more complex polynomial regression, and interpolation like linear or cubic splines for estimating values between known data points, filling gaps. Python libraries handle this smoothly.
And optimization. Finance is full of optimization problems. Best portfolio, best strategy.
Absolutely. Optimization is key. Python libraries can handle various types, from simple convex problems to more complex global optimization. Finding the portfolio with the highest expected return for a given level of risk, that's a classic optimization problem.
What about integration? I remember that from calculus.
Yeah.
How's it used?
Crucial for valuation, especially derivatives pricing. Often, the fair price of an option is expressed as an expected value under a special risk-neutral probability measure. Calculating that expectation often involves numerical integration.
Yeah.
And what's really neat here is Python's SIMPy library for symbolic computation.
Symbolic, as in it does algebra.
Pretty much. SIMPy can manipulate mathematical expressions symbolically. It can perform differentiation, integration, solve equations, all using symbols, not just numbers. This is incredibly useful for deriving analytical formulas, checking results, or even interactive financial analysis.
That's powerful. Now, finance is also inherently uncertain. Markets are random, unpredictable to a large extent.
Yeah.
How does Python handle modeling this randomness? The field is stochastics.
Right, stochastics is vital. It starts with generating random numbers that follow specific distributions. Python's libraries, especially NumPy, make it easy to generate random numbers from, say, a standard normal distribution or a log normal distribution, which are often used to model asset returns.
And these random numbers feed into models of how things change over time.
Exactly. They're the building blocks for simulating stochastic processes. These are mathematical models for systems that evolve randomly over time.
Like stock prices.
Precisely. The classic is geometric Brownian motion, often used as a simple model for stock prices. Then there are more complex ones like square root diffusion models, sometimes used for interest rates or volatility, and jump diffusion models that allow for sudden, large jumps in prices, which we definitely see in markets.
And when you run simulations using these processes, like Monte Carlo, they can be slow, right?
They can be computationally intensive, yes. Hilpish also covers variance reduction techniques. These are clever tricks like using antithetic paths or moment matching to get more accurate simulation results with fewer simulation runs, making them more efficient.
And the ultimate goal of these simulations in finance.
Often valuation and risk measurement. Simulation is crucial for pricing complex derivatives, especially European options, and even more so for American options, which have that early exercise feature. The Longstaff-Schwartz algorithm is a key simulation-based method for those.
Right.
And it's vital for calculating important risk measures, like value at risk, VR, estimating your potential downside loss, and credit valuation adjustments, CVA, which accounts for the risk of a counterparty defaulting on a derivatives contract.
Okay, switching from randomness to analyzing historical data statistics. A big assumption in classic finance theory is that returns are normally distributed. How do we check that?
Yeah, that normality assumption is everywhere, but often doesn't quite hold in reality. Python provides tools for normality tests. You can create histograms or QQ plots to visually inspect the distribution and run formal statistical tests like Shapiro-Wilk to quantify how likely the data is to have come from a normal distribution.
And beyond testing assumptions, what about core financial theories built on statistics?
Well, a cornerstone is modern portfolio theory, MPT, developed by Harry Markowitz.
The diversification guy.
Exactly. MPT is all about how diversification reduces risk. It uses mean variance optimization to find portfolios on the efficient frontier, those offering the highest expected return for a given level of risk, or the lowest risk for a given return. The Shop ratio comes out of this, measuring risk-adjusted return. Python libraries make implementing MPT calculations quite feasible.
Are there newer statistical approaches gaining ground in finance that Python also handles?
Definitely. Bayesian statistics is becoming increasingly popular.
Bayesian. How does it differ?
The core idea is updating your beliefs. Instead of assuming fixed parameters, Bayesian methods start with a prior belief about something, like market volatility, and then update that belief as new data comes in, resulting in a posterior distribution. It's a more dynamic way of thinking about uncertainty.
So it learns over time.
In a sense, yes. For example, Bayesian regression doesn't just give you a single best fit line. It gives you a distribution of possible lines, reflecting the uncertainty. Python has excellent libraries like PyMC for Bayesian analysis.
And all this math and stats, how
Yeah.
does it connect to the absolute cutting edge, like AI in finance?
It feeds directly into machine learning in finance.
Hmm.
ML algorithms are essentially sophisticated statistical tools. You have supervised learning, like classification, is the stock going up or down, or regression, predicting the exact price, and unsupervised learning like clustering, finding groups of similar assets or market regimes.
And what are they used for?
All sorts of things. Pattern recognition and market data, feature engineering, transforming raw data into useful predictors, forecasting market movements, risk management, fraud detection, generating trading signals. Python is, again, the dominant language for implementing ML in finance, thanks to libraries like scikit-learn, TensorFlow, PyTorch.
Okay, that's a really thorough look at the foundations: data, speed, math, stats, ML. But theory is one thing. Hilpish spends a lot of time on real-world making this concrete. He uses connecting Python to the FXCM trading platform as an example.
Yes, that's a great practical example. It shows Python isn't just for offline analysis. You can use libraries to connect directly to a broker's API, like FXCMs.
What can you do through that connection?
You can pull down historical price data, stream real-time quotes, check your account balance, manage positions, and even place trades programmatically. It demonstrates Python's role in building actual automated trading systems.
And if you build a trading system, you have to test it. Back testing.
Absolutely crucial. You don't want to risk real money on an untested idea. Vectorized backtesting, using tools like Pandas and NumPy, is the efficient way to simulate how your strategy would have performed on historical data. You can quickly test variations of strategies, like different moving average lengths.
But there's a catch, right? Just because it worked in the past.
Exactly. You always have to contend with the random walk hypothesis, RWH.
The idea that market movements are basically random and unpredictable.
Pretty much. The RWH is a tough benchmark. Any strategy you develop has to demonstrate that its performance is statistically unlikely to be just luck, that it genuinely captures some market inefficiency or pattern better than a random guess. Backtesting helps assess this, but it's not foolproof.
But can machine learning help overcome that randomness, or at least find subtle patterns?
That's the hope, and where a lot of research is focused. ML-based strategies try to learn predictive patterns from vast amounts of data, price data, news sentiment, alternative data to forecast market direction or volatility.
Okay, so you have a strategy, maybe ML-based, it looks good in backtesting. What about managing the money itself? How much do you bet?
Now that's a critical piece. Capital management. Hilpish discusses the Kelly criterion.
Kelly criterion.
Yeah.
Sounds important.
It is. It's a mathematical formula that, in theory, determines the optimal fraction of your capital to allocate to a particular bet or investment to maximize your long-term wealth growth. It balances potential return against the risk of ruin. It directly informs decisions about optimal leverage. Using too much leverage can blow up an account even with a winning strategy.
So it's not just about being right, but betting the right size.
Exactly. Risk management is paramount. Beyond just returns, you need to analyze the risks of your automated strategy. Key metrics include maximum drawdown, the biggest loss from a peak to a trough during the backtest, and value at risk, VAR, estimating potential losses under normal market conditions.
And once you're ready to go live, put in the algorithm on a server.
Then deployment considerations become vital. Things like robust logging, recording everything the algorithm does, and monitoring its performance in real time are essential, especially if it's running on a remote server somewhere. You need to know it's working correctly and be alerted if something goes wrong.
Okay, shifting from trading to another huge area, derivatives, options, futures, swaps. Hilpish introduces a specific Python application he built, the DX package.
Yes, the DX Analytics package. It serves as a fantastic, concrete example of building a reasonably complex financial application in Python, specifically for pricing derivatives using Monte Carlo simulation. It's built step by step using object-oriented programming.
OP.
And it's grounded in theory.
Absolutely. It relies on the fundamental theorem of asset pricing. That's a cornerstone theorem in mathematical finance. It essentially provides the theoretical justification for risk-neutral valuation, the idea that you can price derivatives by calculating their expected payoff in a hypothetical world where all assets earn the risk-free interest rate, and then discounting that back to the present.
Sounds abstract, but it lets you price things consistently.
Exactly. It provides a coherent framework.
Yeah.
So the DX package uses this theory, implemented via Monte Carlo simulation, to value derivatives.
What kind of derivatives can it handle? It demonstrates valuation for both European options, which can only be exercised at expiry, and American options, which can be exercised early. And it calculates not just the price, but also the Greeks.
Ah, the risk sensitivities. Delta, vega.
Precisely. Delta measures how the option price changes with the underlying asset price. Vega measures sensitivity to changes in volatility. These are crucial for hedging and risk management.
And because it's built with OOP, it can handle more complex situations.
Yes, that's a key benefit Hilpish highlights. OOP makes it easier to model portfolio valuation. You can create portfolios containing multiple derivatives, potentially exposed to multiple correlated risk factors like different stocks, interest rates, FX rates, and value the whole portfolio consistently.
Can it connect to real market data too?
Yes, he includes a very interesting case study on market-based valuation. This involves calibrating the model, adjusting its parameters, like volatility, so that it reproduces the observed market prices of traded options, say on the DAX 30 index.
Why is that important?
Because it gives you market-consistent valuations and risk measures. Even if your model isn't perfect, if it's calibrated to the market, its prices for other non-traded derivatives or its risk calculations are more likely to be relevant and useful. It shows how simulation frameworks like DX can provide results comparable to analytical formulas where they exist, but can also handle much more complex situations where formulas fail, even though there's heavy computation happening underneath.
Wow, okay. We've covered a lot of ground there. A really deep dive into Python for finance. We started with that sheer flood of data driving modern finance.
Yeah, and how Python's become the go-to tool. We looked at its basic building blocks, the data types, the structures.
Then how to make it fast. Factorization, NumPy, Python, multiprocessing, handling I/O with tables.
Right. And then the core math, stats, and stochastics approximation, optimization, simulation, handling randomness, testing assumptions, MPT, Bayesian ideas, and linking it all to machine learning.
And finally, seeing it all come together in real-world applications like automated trading backtesting, the Kelly criterion, risk management, and that detailed look at derivatives analytics with the DX package.
Absolutely. I think the main takeaway is that Python provides this single, powerful, consistent environment. You can go from idea to prototype to complex modeling to backtesting, even to live trading and sophisticated derivatives pricing, all largely within one ecosystem. It really puts tools that used to be, the exclusive domain of rocket scientists with complex C++
Right
libraries.
at your fingertips.
Yes, exactly. Much more accessible.
So to leave our listeners with something to think about, as these financial markets just keep evolving faster and faster, driven by more data, more AI, what new frontiers, what new possibilities will Python help you explore? The potential for discovery here, it feels like it's really just beginning.